want to mention that some of the material included today was presented this summer at the NAM 28 conference in Providence and at EuropaCat 2023 in Prague. I also want to recognize my collaborators for this work, Dr. Jeff Kinvan and Dr. Luca Lucarelli of Micromeritics. For many years, mercury intrusion porosimetry has been used to investigate not only the accessible pore volume as a function of pore window or throat size, but also to provide insight into pore structure with permeability, tortuosity, and diffusion calculations. Over the years, attempts have been made to interpret the pore structure, such as intrusion-extrusion cycling and the Reverberi method. For this study, we used the Micromeritics Autopore, a high-resolution mercury porosimeter, to investigate a new method for high-resolution differential scanning porosimetry, DSP. For this work, we selected 5 commercially available catalyst supports, 4 alumina and 1 titania, with different pore size distribution types. Note that similar analyses can be performed with pharmaceutical tablets, EV battery electrodes, soil and rock samples, basically any material with a pore structure consisting of pore cavities filled through smaller pore throats. Such pore structures are common when the porous material is manufactured, industrial or natural, by the compaction of powdered material. Here we see a general description of the pore size distribution type, along with the BET surface area and skeletal density, determined separately by gas adsorption and gas displacement, respectively. With classical mercury intrusion analyses, the sample and holder are evacuated and filled with mercury at low pressure. Low pressure data, up to a few atmospheres absolute pressure, is collected often in a portion of the instrument optimized for this pressure range, and then up to much higher pressures in a portion of the instrument better suited for analyses at these higher pressures. Intrusion volumes are collected as a function of applied pressure over the entire range, low pressure and high, according to programming of the analysis protocol. In addition, the volume extruded from the sample is often recorded as the pressure is reduced back to atmospheric. Here we see examples of the cumulative intrusion volume per gram of sample under test for the 5 catalyst supports, with intrusory summary data provided, including total percent volume, total percent porosity, pore size corresponding to 5% and 95% of the total intrusion volume, that is, the 5th and 95th percentiles, the median diameter of the distribution, which is the 50th percentile, the modal pore diameter or diameters, that is, the local maxima in the distribution, the pore area calculated from mercury porosimetry analysis, the apparent skeletal density calculated from the highest pressure in the analysis, where it is assumed that all pores are filled. Now we see both the intrusion and extrusion analyses of one of the alumina catalyst supports, which we characterize as having a coarse, broad pore distribution. Note that when the pressure is reduced to 1 atmosphere during extrusion, a significant volume of mercury remains in the sample. That is, not all the mercury intruded into the material is able to be extruded even at lower pressure. Generally, when pore cavities are filled through pore windows or throats that are smaller than about 3 to 5 times the size of the cavities, it is unlikely that all the mercury will extrude from the cavity when the pressure is reduced. The volume in the throat should, but not necessarily that from the cavities. Next, we see the intrusion and extrusion analysis results for another alumina catalyst support, this one with a broad bimodal distribution of pore sizes. Note that the extrusion analysis shows us that some of the mercury is trapped within the cavities once again, but that most of this is in cavities that were filled through larger pore throats, the mode to the right of the graph, but not so much for the smaller pore throats in the mode to the left of the graph at throat or window sizes less than 100 nanometers. We can see this as the extrusion curve approaches the intrusion curve closely at the cumulative intrusion volume of about 0.5 milliliters per gram. The intrusion-extrusion analysis of this alumina catalyst support with a fine, narrow pore size distribution indicates that even when looking at pore window sizes an order or two larger than those corresponding to the pore filling, we still don't see all of the mercury extruding. The fact that the extrusion curve is flat from just under 100 nanometers to almost 10,000 nanometers supports the belief that the mercury intrusion into some of the cavities truly is irreversible. For this analysis of our last alumina catalyst support, described as showing a medium narrow pore size distribution, a large proportion of the intruded mercury remains within the sample as the pressure is reduced to atmospheric. Compare that to the analysis results for the alumina catalyst support with a similar intrusion pore size distribution. Very little mercury remains trapped within the sample. Apparently, these last two materials, even though showing similar intrusion volumes versus pore throat or window size, have significantly different pore cavity distributions. These results indicate that the cavities in the titanium sample are probably smaller than those in the last alumina sample, even though the throat sizes seem to be about the same. Looking only at the extrusion curves and scaling them to a percentage of the total intrusion volume, an overlay of the relative volume retained shows quite a bit of difference between these materials. As we just saw, the titanium showed the smallest amount retained, that is 7.3% of the total pore volume, while the coarse broad alumina, 5102, showed the largest total retained, almost 35% of the total amount of mercury intruded. Is there some way that we can better characterize these materials using mercury intrusion analysis to gain some perspective into the volume of pore cavities being filled as a function of pore window size and separate that from the volume of pore throats filled, with the throats having the size of the window through which the cavities are filled? When we speak of pores being filled through windows or throats, we generally interpret the pore structure as a bundle of parallel cylindrical capillaries. We see a certain volume filling through an opening of a size that can be calculated from the applied pressure. We don't know anything about whether the pores are interconnected or of some shape other than a cylinder, maybe that of an ink bottle. If we want to calculate liquid permeability or gas diffusion rates from these intrusion results, the values may be incorrect for complex pore structures. I mentioned the ink bottle pores as that is one of the traditional explanations for hysteresis between intrusion and extrusion curves. The pore fills through a narrow throat at the pressure corresponding to the intrusion pressure, filling not only the throat but also the bottle or cavity behind it. During extrusion, the throat empties at the same pressure at which it is filled, but the cavity does not empty until the pressure that corresponds to its larger diameter, that is, a lower pressure. Now, as we have just seen, sometimes all the intruded mercury does not come out during extrusion, particularly when the cavities are greater than about 3 to 5 times the size of the pore window or throat. Now, the ink bottle model is probably an exaggeration of the true pore structure, which could be, in fact, a set of interconnected pore cavities connected to one another through several pore throats. In 1965, Reverberi and others published a technique that can be used to try to provide the volume of pore cavities of different sizes filled through pore windows, again of different sizes. The result can be illustrated as a three-dimensional plot of pore volume as a function of both cavity size and throat size through which the cavities are filled. For this technique, the test specimen is first fully saturated with mercury by performing a stepwise intrusion analysis up to the maximum desired applied pressure, filling even the smallest pores present. A stepwise extrusion analysis back to atmospheric pressure follows, then analysis stepwise back up to maximum pressure. Now additional extrusion and intrusion cycles are performed, with each cycle extruding down to progressively lower pressures. So for the first of these cycles, the pressure is only reduced slightly, then pressurized back to the maximum pressure, all following the same stepwise spacing of applied pressures. For the next sample, the pressure is reduced slightly more, followed by repeated intrusion back to maximum applied pressure. The process then continues for each cavity size to be characterized until finally returning to atmospheric pressure. Now, it is assumed that one interval cavity size is being refilled at each repeat intrusion, and that the cavity size interval is that which corresponds to the largest pore throat through which it is refilled up to the lower cavity size of the previous interval. Thus, the cavity size cannot be less than that of the smallest throat through which it is being refilled. Note that due to the number of intrusion and extrusion cycles, the reverbery method is a bit time-consuming. While it does present a three-dimensional pore distribution, the results are a bit difficult to use for improving permeability and diffusion calculations, as we do not have a separate pore size distribution for the throats, and it does not take into account the mercury retained in the cavities that are assumed in some cases to be as small as the throats through which they are filled. The current investigation was undertaken to try to provide high-resolution distribution of pore cavity volume as a function of pore window or throat size, as well as a separate pore throat distribution, again using intrusion and extrusion cycles, but this time not initially saturating the test specimen with mercury, but rather building up the intrusion-extrusion cycles from low pressure. Now, we performed a complete pore size distribution analysis to determine at which pressures the pore volume is intruded so that we can focus the intrusion analysis over those pressures. The intrusion-extrusion analyses shown at the beginning of the presentation were those preliminary analyses. We selected target pressure values to provide about 20 pressure intervals. More intervals provide more resolution in the cavity and throat distributions, but require longer to perform. Analyzing a fresh test specimen so that mercury has not already been trapped in some of the larger cavities, as is the case with the reverbery method, we collect intrusion data up to the end of the first desired interval, and then extrude in a single step back to atmospheric pressure. The cycle repeats up through the next desired interval and back to atmospheric pressure. The process continues until all intervals have been collected. Here we see the first 7 intrusion cycles for analysis of one of the alumina catalyst supports using the DSP method. The first intrusion cycle starts from vacuum pressures up to about 25 megapascals. The first extrusion is back to atmospheric pressure. Note that not all of the mercury extrudes, as almost 0.03 milliliters per gram of mercury is still within the test specimen. The second intrusion cycle is up to about 35 megapascals, and the second single point extrusion is again back to atmospheric pressure. Again, we see that some of the mercury intruded remains in the sample when pressure is reduced to atmospheric for this second cycle. As this is in cavities that were not filled in the previous cycle, we see additional retained mercury. The third intrusion is up to about 50 megapascals with extrusion back to atmospheric pressure. The analysis continues until all desired cycles are completed. Note that the volume retained continues to increase with each cycle. It is this retained volume that gives us insight into the cavity volumes. It is the intrusion pressures and corresponding window sizes that give us the cavity volume distribution as a function of pore window or throat size. For the pore volume of the throats, it is simply the total new volume intruded less the volume assigned to the cavities. We are not necessarily finding the cavity sizes, but rather the volume of the cavity filled as a function of throat size and a separate pore throat distribution. Looking first at the alumina with coarse broad distribution, the classical intrusion-extrusion analysis is shown here in blue with summary data in the first row of the table. The complete DSP results are shown in green, and notice that these results are like the classical intrusion analysis, though with higher resolution and as a result better equilibration. The intrusion of cavity volumes as a function of pore windows through which they are filled is shown in yellow, while the distribution of throat volumes is shown in orange. Here we see what is likely some surface cavities filled initially, then the interconnected internal cavities filling. If we add up the volumes shown in the cavity distribution to those from the throat distribution for a given window size, it will give us a total intrusion volume for that window as shown in the green curve. The summary results for the DSP analysis are shown in the second row of the table. Since the permeability and diffusion are a function of the volume of the interconnecting throats, we would expect the calculated values to be different depending on whether the classical intrusion is used or the DSP throat distribution, due to differences in volume assigned for given pore window sizes. Compare the orange and green curves. Here we see the log differential curves for the cavity distribution in yellow and the throat distribution in orange. We can clearly see the difference in the distributions and see that there is more volume in the throats than there is in the cavities, and that some of the cavities are filled at lower pressures, larger diameters than the throats. A few things become obvious when comparing the classical MIP analysis in blue with the DSP throat and cavity distributions in orange and yellow respectively. First, we do see that both methods produce a bimodal pore volume distribution. Closer inspection of the DSP results indicates that while there are throats and cavities present at larger sizes, the volume intruded into smaller pore windows is almost exclusively contained in pore throats, or at least is mostly reversible intrusion, which indicates that the throats and the cavities are about the same size. There is very little mercury retained at the higher pressure corresponding to smaller pore windows, whereas there is quite a bit of retained mercury for the larger pores. Since it is likely that the smaller pores contribute most to the diffusion rates and permeability, the values calculated using classical MIP analysis and DSP analysis will be somewhat similar for this bimodal material. The log differential graphs make it easy to see that most of the cavity volume is filled through the larger pore windows and not much through the smaller ones on the left-hand side of the graph. Recall from the classical MIP analysis of this alumina with a fine, narrow pore distribution that not much mercury is retained. As expected, the DSP analysis only returned a small cavity volume distribution, where most of the pore volume is in throats. There will likely be only a small difference in permeability and diffusion rates calculated by the results of these two analysis techniques. The log differential graphs reflect the small proportion of pore volume within cavities for this sample. For this alumina catalyst support, the throats and cavities fill pretty much at the same pressures, though the volume in cavities is significant. So these cavities are significantly larger than the throats as much of the mercury is retained within the pore network. Since the throat porosity and median diameter are similar between the two techniques, we expect the permeability and diffusion rates calculated to be similar. And the log differential echoes what was seen with the cumulative results, with a significant volume of mercury retained in the cavities. While the distribution for this titania and the previous alumina support seems similar, note that much less mercury is retained by this material, and so the percentage of the pore volume in cavities is significantly smaller for the titania. The larger throat porosity will likely lead to slightly different values for permeability determined using these two methods. Here we see the very low cavity volume from the log differential for the titania sample. The table shown includes values for tortuosity, water permeability, and ammonia and benzene diffusion for these 5 materials based upon classical MIP and high-resolution DSP analyses. For many, the results are very similar, but by separating the throat and cavity distributions as a function of pore filling window, we do see some significant improvements in results, particularly for the alumina with coarse broad pore volume distribution 5102. Recall that this is a sample for which more than 30% of the intruded mercury is retained within the sample. Note that BET surface areas and skeletal densities from gas displacement were used in the calculations. We have looked at analysis results using the high-resolution differential scanning porosimetry method for 5 catalyst supports and can clearly determine the volume of the larger cavities filled as a function of window or throat diameter. Separation of cavity and throat porosity improves permeability, as it's related to the throat porosity only, and diffusion rate calculations, as it is related to the median diameter of the throats only. Thus, we have a better understanding of the pore structure and volume distributions of these hierarchical materials. And now we see the difference between pore throat and pore cavity filling, and have separate distributions for the pore throats and the pore cavities as a function of throat size.